Hello, this is Intro to Proofs Part 2. We're going to go through notes on this section and then handle the next preview activity. So some notes I want you guys to think about as you read this section is that Theorem 2.5, De Morgan's laws, is really important. I'm going to refer to it as De Morgan's laws from now on. So try to remember that and try to use it. Try to understand what it means because it is something we're going to use a lot in this class. De Morgan's law just comes up again and again. Logical equivalences of conditional statements, that part is also pretty important. So make sure that you're understanding that especially example 2.7, the words in bold, that's also pretty important there. Let's see, and then the logical equivalences of conditional statements, the one that we're going to use a lot is that the contrapositive is the same as the original. Like it is logically equivalent to the original. That's something we also use a lot. Now, methods of establishing logical equivalences. There's two methods. One of them basically boils down to doing a truth table. And one of them, the second one, is one we're going to do more often in the section from now on, is establishing things are true based on previous things we know are true. And then I put a logical equivalences PDF on Moodle. Make sure to check that out. It can help you with your homework. Now we're going to do progress check 2.8. Now, again, don't continue this video until you've actually attempted it. So, what's going on in this progress check? So in progress check 2.8, although it's possible to use truth tables to show that P implies Q or R is logically equivalent to P and not Q implies R, we instead use previously proven logical equivalencies to prove this logical equivalency. In this case, it may be easier to start with the working with P and not R implies Q. So we'll start from the back. So P and not Q implies R is equivalent to this, which is justified by logical equivalency established in preview activity 3.3. Okay, so in 3.3, we had that, let's see. In 3.3, we had that P Q is equivalent. I don't have an equivalent thing. I'll just say equal. You know what I mean. So if I was writing on a whiteboard, it'd be 3 lines for equivalent. Is equivalent to not Q or P. No. Equivalent to not P or Q. Because it can either Q is true or negative P, so it'd be not P, so it'd be vacuously true. So if I apply that here, then in this case, instead of thinking of there being a P there, think of there as being a P and not Q in there, and R is here. So we're just substituting now. So then we have P and not Q plus R is equivalent to not P and not Q or R. Okay, now let's use De Morgan's laws. So De Morgan's law says that move the negative through. So negative P or negative Q well, then double negative. So double negative is positive. Okay. And so I want to get that P, and I'm using ORs. ORs are associative. So then I've got not P or Q or R. Well then, I can use 3.3 again. I can use 3.3 again and get this is P implies Q or R. And so that's how you get from P and not Q implies R to P implies Q or R. And so then substituted in 3.3, and then I use, this is here, this is De Morgan. There. Here we just did double negative. So you always want to justify your statements, your movements of logic. And this is associative. So we know that OR is associative, so we switched the parentheses, and then we did 3.3 again. So that's how we, if we're doing a truth table, all these things would be on the other side, but I kind of ran out of room. All right. Now let's let A and B be integers. Suppose we're trying to prove the following. If 3 is a factor of A times B, then 3 is a factor of A, or 3 is a factor of B. Now, think about that. Think about 3 is a factor of AB as being like P, and then 3 is a factor of A being Q, and 3 is a factor of B being R. Then what we just did is that statement is really the same as P and not Q implies R. And so it's an easy, and this statement right here, this is an easier thing to prove right here, because you get to assume more and only prove one thing. Whereas here you're assuming one thing and having to prove two things. So the proof for this one will be shorter. So you can, this is an example of how we use logic to help ourselves get a smaller proof. These two statements are equivalent, and we're going to prove the one that has a shorter proof, because I always say, in this class especially, try to work smarter, not harder. All right? All right, I'm going to pause the video now, and then we'll continue with the activity 210 in the next video.